Okay, so we'll get started. Again, we're good. My name is Norm Williamson. What we're going over chapter 4 and 5, and we'll go over skill uh, for chapter 4. We'll have a few things going on today. Shouldn't take too long, but we're getting into some things, especially chapter 4, explosion dynamics. Chapter 5 is a little confusing for people if they haven't had a fire background, so we'll cover quite a bit on that too. If you have questions, please ask. Just unmute yourself and ask, and we'll go ahead and get started. So first thing we're going to do is go over chapter 4, explosion dynamics. Let's make sure we're recording. Yes, okay, we're good to go. So what we're going to do in explosion dynamics, number one, is we're going to understand the basic science of explosions and the types of explosions and basic documentation of explosions, and then we're going to figure out the different types of explosions, determine the epicenters, and the causes for different types of explosions. We'll cover mechanical, we'll cover chemical, we'll cover detonation and deflagrations. There's usually a little confusions between those. We'll go over high order and low order explosion damage, that kind of thing, and then effects caused by explosion, blast waves and so. So we'll go over levies, seeded explosions, non-seeded explosions, gas vapor explosions, dust explosions, that kind of stuff. First, we're going to start with mechanical explosions. What these are just conversions of mechanical or chemical potential energy. When you look at potential energy, what potential energy, quite simple, is if you have a balloon that's full of air and you let go of the balloon without it being tied up, your air is inside the balloon is potential energy, and when you let it go and the balloon moves, that's kinetic energy. Quite simply, you're causing the energy to move is what kinetic energy is. Okay, that's the easiest way to explain the difference between energy moved into kinetic energy, potential energy to kinetic energy. When you see explosions, there's usually a blast pressure front that can cause damage to structures, structural members, that kind of thing. So they're quite dangerous. And you might find secondary fires away from the original point of ignition, depending on what type of explosion you have. Sometimes there's complete destruction of the container around the explosion, container being a room or a house or something like that. And I'll give you a good example. I was at a terrorist bombing class in New Mexico. If you ever get to go there, it's really cool. But we built a 500-pound ANFO bomb, ammonium nitrate bomb, like the Spalding ammonium nitrate, or the huge ammonium nitrate fire that was in West Kama, Texas, not West Texas, but West Texas, a few years ago that blew up half the town. Well, we built a 500-pound bomb and put it in the trunk of a car. The college built a small house next to the car, 50 feet away, and we were a half mile away behind a big sheet of what is it, bulletproof type glass. When we set that bomb off, just 500 pounds, mind you, the potential energy that was in there literally blew the car apart. The only thing you could find was a transmission housing and an engine block. Literally, that's all you could find. A half mile away, behind that glass, there were parts from that car hitting that glass a half mile away. And that house that was there was no longer there. The blast wave blew the house down. And that was just 500 pounds. So think of ANFO and think of the Murrah building in Oklahoma City. When McVeigh blew the Murrah building up, he had 7,000 pounds of ANFO when he blew that building up. So think of how much difference it could be. Just kind of throwing that out there. So when you look at blast pressures and destruction, that's going to make a difference in what type of explosion you have. Mechanical explosions, basically, they're a result of an increased pressure inside a confined container. Quite simply, like a levee, like oh, what is it? Anything that will blow out because of the pressure inside. If the pressure's exerted into the container, if it's higher than the capacity of the container, basically it'll rupture, it'll disintegrate. Uh, how many people have ever thrown a beer into a fire when you're camping and get drunk? I know it's kind of rough, but or a Coke can or anything like that. What it'll do is it'll expand until it opens, won't it? Because the pressure in it builds up. So we have to think of those that's what you're looking at, a mechanical explosion, because it gets to boiling inside and it starts expanding. And once it loses uh, once it loses enough capacity inside that container, then it opens at the weakest point is what it does. So the pressure exerted to the container is greater than the structural capacity is what it is. The gas of the material does not go through a chemical change directly. It's caused by the pressure. Is what causes the damage in these in mechanical explosions. They don't require combustion or ignition source, anything like that. But it's basically the most common thing you would see in this type of explosion would be a levee, of course, mechanical explosions. Now, chemical explosions are a little different. Chemical explosions, they have a real fast exothermic reaction. Basically, the ignition source it initiates, and what happens there is an increase in temperature can cause it to self-initiate. For instance, nitroglycerin, something like that. The explosion and the combination together with the blast pressure front, it pushes out in all directions. So therefore, you're going to have a different type of reaction than you would a levee, that kind of stuff. The fuels they go under they go under a chemical change, and basically in that reaction you have an explosion. Most common things are like LP gases, dust explosions, uh, solid fuels like ammonium nitrate, uh, and then under chemical explosions you also have deflagrations and detonations. Where a mechanical explosion, you don't have a detonation or a deflagration. You have an explosion. The difference is the deflagration and detonation. It takes more than just pressure for that to happen. Basically, a deflagration, it's a chemical reaction that gives a huge heat and sparks or even flames and moves through the material at less than the speed of sound. That's what a deflagration is. The difference between it and a detonation are the pressure release rate of the fuel, basically. And the deflagration is a lot slower than a detonation, with the reaction traveling less than the speed of sound. So therefore, I always tell people the best way to think of it is think of it as a boom and a kaboom. When you see a uh, a and that's what I call. We'll go into that here in a bit, but it's the difference between low order and high order. You might hear kaboom or boom. We'll go over that in a minute. But the most commonly involved gases they're suspended in the air, and the flames travel insofar as the flames travel through the fuels, depending on the density of the fuel, which way is easiest for it to go. That's why you might see a pattern go around a corner or something like that on a blast pressure because of the way it's made. Uh, Generally, the higher the fuel's pressure, the explosion reaction is bigger. It's that simple. And that's what is involved in a deflagration. Deflagration basically high heat sparks flame, that kind of thing, and moves through material less than the speed of sound. Where a detonation is a supersonic thermal decomposition, and it has a shock wave, and the shock waves caused by the decomposing material. And explosions with energy fronts travel faster than the speed of sound. So when you get a detonation, and I'll put it quite simply, you normally would hear boom, where and I know this sounds stupid, but listen to them online, you'll understand. When you hear of a deflagration, you're going to hear more of a kaboom. You see, because the reason being is it's moving slower than a detonation. So just kind of throwing it out there. Characteristics of a detonation, basically, they're usually high explosives, solid fuels, oxidizers, and basically they're under some type of pressure usually. They have a shock wave, which is a blast pressure that moves faster than the speed of sound, so you can't get out of the way, and basically the sound wave travels through solid objects and through the ground. Basically, that's why you get blast pressure like seismic reactions on detonations and that kind of thing. And they're usually fuel and oxidizers under pressure, and the shock wave causes a lot of physical damage. It can occur where, like, levees that have flammable liquids, LP gas tanks, we've seen those, can occur in diffuse gases that are under pressure. Gas explosions. I'll give you a good, for instance. When I was working at Herman Life Flight, we made an explosion in Brenham, just outside of Brenham, and what it was an LP gas explosion. Well, what ended up happening was the LP gas went down, and when a car drove down into this low water crossing, it got into the gas. Well, it followed it back to the original tank, and both exploded. Well, when you saw this, it was a combination of a high pressure and low pressure explosion, which we'll get into those here in a minute. But what ended up happening was it looked like from above there were houses moved off the foundation, which was low pressure, but then you had things that were splintered everywhere, which was high pressure. So that was a combination. But the whole idea is that it's gas under pressure that causes these detonations, that kind of stuff. As far as low order damages, you have classifications for different types of damage. You have low order characteristics, which are usually non-seeded explosions and deflagrations, both. You can have both of them there. And when you see that, especially on buildings, that kind of thing, you'll see the walls will be bulged out a lot of times at the bottom. They'll bulge away and fall, or our walls will fall out. If anybody's looked at the skills sheet that we put out there, you had a picture with walls bulging. You had a picture walls falling out, that kind of thing, and they fall out while the structure remains intact. The roofs might come off the building a little bit. Windows might be broken or moved out of their frames, and there's a lot of debris, but it's over a short area. And inside those, you'll find fire inside whatever it might have been that blew up. And those are what are low order explosions. High order explosions, now, they usually have a seeded area and a detonation. Walls, basically, they're shattered, they're splintered, that kind of thing. And your debris is going to be small and spread way out, and basically the structure might be completely destroyed. Here's the thing, though: you might find fire on the periphery because the blast pressure push the fire out. There's a photograph in the in that skill too of a high order explosion, and when you look at it, you'll see all of it splintered, and you'll see like a crater type thing inside this building, but things on the out, and there's debris all the way back across the road. But when you look at it, there's also burned trees on the outside of the building. So that's what notes that it's a high order explosion or a detonation, that kind of thing. Everybody with me so far on that? Cool.
Yes.
Must mean I'm explaining it well, or else you don't want to say anything. Either way is fine with me. You say it's good, it's good. So the effects of explosions, basically you have blast pressures which destroy most of the stuff. Blast pressure front, it's usually there's a big quantity of gases that are made, and they expand real fast from the area of origin. That's why you see photographs of people that go into a house, stand in front of the fireplace, and might a light a cigarette or something, and it sure, it'll burn them and hurt them, but it might kill people behind them because that blast pressure is what's killing them. The gas expands fast, real rapid from that area of origin. So it's not going to be as much right there at the area of origin, but it's going to be the more there's going to be more concentration of a blast wave behind it. It creates blast pressure front that goes outward from the center. So if you're the one that's blowing it up, if it doesn't kill you, it's going to kill somebody around you, that kind of stuff. Pressures, basically, as the blast pressure front goes further away, though, from the center, once you get to about 50 feet or so, as it goes away, it starts diminishing, starts going down. And basically, that's the primary reason that there's injuries, is that blast pressure. Now, and I'm going to throw this out there. You have two different blast fronts, though. You have a positive pressure that goes out, but then you have a negative pressure that comes back, and that's what makes it difficult to determine sometimes that you had an explosion, because it'll push things out and then it'll bring it right back to where it was, that kind of stuff. So it's something that you might or might not see. The blast pressure fronts are like I say, the primary reason that people get hurt and damage and that kind of stuff. Then you have deflagration pressure fronts, and what they do is it's not part of an explosion reaction. Remember, deflagrations are slower than detonations, so therefore your detonation blast is you're going to find low order. I'm sorry. Your deflagration, you're going to find low order damage. Basically, the blast front goes through and expands the gas and the surrounding ignition source, which basically, when you look in pictures, you might find, or do a fire scene, you might find walls bulging or falling out, that kind of thing. But you'll still see inside that there's still studs standing, that kind of stuff, and so on. And then this is the one where you could get two blast pressure fronts, basically positive and negative pressures, that kind of stuff. Now, when you look at, we have videos, and if you're looking at the videos on the website, there are several videos on blast pressure and on different types of blasts and so on. So it's a great idea. Look at those videos that we put on there, because they'll show you what they look like. It's not an easy thing to understand if you don't look at it, that kind of stuff. So therefore, look at those. Use what we give you there. Positive pressure phase in the portion of an explosion in the deflagration. Basically, the gases expand outward. So think of that. And the negative pressure, basically, it comes back into that center. So you can get people injured going out and coming back in. You get damage going out and coming back in a deflagration type explosion. basically most of your injuries and damage is, of course, going to be going out, because your blast pressure wave coming back in is not going to be as strong. It might You might have additional damage coming back in, yeah, but it's not going to be as bad on the rebound. As far as ventilation and explosion characteristics, the ventilation in a confined space, they'll affect the blast pressure front. Remember, pressure will take the least amount of it'll take the easiest way out, I guess is the best way to put it. Your pressures, so if you have a hallway, it might go around if it doesn't blow over the wall. If you have a big cinder block wall, your blast pressure might go that, or if you go around that, something. I'll give you for instance. There's some things over on the west side of the county that have nuclear things that they store, nuclear bits and things like that. Well, they're required to put those underground, but the walls inside this building have to be blast proof. So what they are concrete walls, and as you go in, they kind of zigzag like this. That way, if it does blow up, your blast pressure will not come out as easily. Does that make sense? So therefore, it's going to take the path of least resistance. Is what it's going to do. So let's see. So ventilating, if you have openings, it's going to go through that first. Your damage might occur because of ventilation and weaknesses of whatever vessel you have. Vessel being if it's like a compartment or a home or something like that. As insofar as shrapnel fragments, that kind of thing, what shrapnel is basically, it's small pieces of debris thrown from a container, and basically, or a structure that's ruptured, and it's restricted to the blast pressure more than anything else. Remember, I told you earlier about the about the info bomb. Like I say, we were more than a half mile away from a small 500-pound bomb, and this thing, I mean, it blew debris all the way up there. So when people say, there's just no way, if you're inside an urban area, there's no way you're going to be able to accurately secure an area that big. So you have to think about that when you're looking at it. But it can cause injuries. Shrapnel, I've already said that. Exposure can cause secondary damage by rupturing gas lines, electrical wiring, that kind of stuff too. So you might end up with a fire caused by the explosion itself. So you have to think like that. And then you have, with the shrapnel, the small debris, you also have seismic effects. Seismic being basically earth moving, that kind of stuff. Does somebody have a question? Or you just like me that much you wanted to clap or something? Just checking. Okay, so seismic blast effect is basically a blast near, it's at ground level, basically, within a few feet of ground level. And it creates an air blast that causes the ground to shock. It's usually referred to as the seed of the explosion. When that blast occurred in Brenham, like we were talking about, the seismograph in Houston picked it up as it could have been about the same as a a number 3 earthquake. I forget what that's called, but the seismologists, they recorded that, and it shook buildings in downtown Houston. So the whole idea is you can have a seismic effect from that. It's basically the earth vibrating like an earthquake, and shockwave as the shockwave goes across the ground, that kind of thing. The distance of the shock wave is dependent on the size of the explosion and the type of earth that's there. I mean, we got to think about where we're at. It's going to travel a lot further here than say it would up in the Smoky Mountains, isn't it? Because we have a flat, we're in the plains area down here. Seismic effects that are associated, they're usually with large seeded explosions, like a detonation, and well, you have to think of things too. I mean, you can get seismic effects from buildings falling, any number of things. Then we talk about thermal effects. The thermal effects, it's basically explosion heating the surrounding area, quite simply. Uh, the thermal energy that has, it ignites the gases and the air and that kind of stuff. The heat from the explosion ignites combustibles, of course, and detonations produce a huge amount of heat. But the heat duration is real fast, so it doesn't affect the exposures right there. So think about that. When a detonation goes off, look at the photograph where a detonation is. You'll see fire outside, but not inside, because yeah, they have a lot of heat, but the duration is so fast that it won't ignite the exposures, that kind of thing. As far as thermal effects on shrapnel and that kind of thing, shrapnel can cause major damage and that kind of stuff to the surrounding areas. And secondary fires a long ways away can happen from the seat of the explosion because of the heat to the shrapnel, that kind of stuff. The deflagration is more likely to spread to fire to surrounding combustibles, that kind of stuff. And the flame front at high temperature, but unlike detonations, the flame front moves slower, so therefore your deflagration is going to leave fire damage, that kind of thing. So you when you examine an explosion scene, those are what makes it a little easier to figure out. It's not always that way because you can end up having two separate type explosions. Not that it happens very often, but it can. And think too, you can have fireballs, that kind of stuff that come out of that, and it's fires that's suspended in air by the ignitable gases and that sort of stuff. And occurs during or after an explosive explosion. But and you can see that sometimes too. It's real prevalent in things like levees for LP gases, that kind of thing. Radiant heat can contribute to secondary fires, injuries, that sort of thing. Now, the different types of explosions we're going to talk about too are seeded explosions. As far as we'll talk about the seeded explosions, what the characteristics of them is they have an epicenter. They're easily identifiable, basically because there's a crater, there's a hole where that seeded explosion occurred. I never thought about that up until when I first became an arson investigator. When I was a kid, we lived up in the hill country, and we used to drop a quarter stick of dynamite in a hole that we dug in order to dig out septic tanks and that kind of thing. Well, it left a crater. Never thought about it, but dynamite, it was a seeded explosion. So you'll have a hole of some type. The epicenter is the center of the seeded explosion, and it's at the center point of the seismic shock that created the wave. Basically, the size of the epicenter is basically whatever. It depends on the size of the blast, really, the explosive blast. Chemical explosions, they're supersonic, faster than the speed of sound. Speed of sound, by the way, is 1,100 feet per second. If anybody's interested in that, but it's faster than that. And if you can move that fast, see if you can run away from it. I can't move that fast. Let's see. The next thing we'll talk about is blevies, and blevies, it's a boiling liquid expanding vapor explosion. That's what it's an acronym for. It was after basically the liquid boils inside and increases the pressure inside a container, inside a vessel, that kind of thing, and until it exceeds the vessel's structural limitations. Now there's things on these structures a lot of times that will have like blow off valves and that kind of thing. But once once the pressure exceeds what can blow off, you can end up with a blevy, that kind of thing. As far as the physics of a blevy, most of them occur with LP gases, that kind of thing. Uh, Normal atmosphere like we have, it's usually stored under pressure anyway, and it takes less time for the liquid to boil and basically it destroys the canister or vessel or whatever it's in. I've seen a few blevies that involved. I've seen done investigations on gas grill tanks that exploded, and they do cause some damage. I'll guarantee you that. There's a video out that of a just a small 15-pound LP gas tank that would the fire was there was so much fire that it would fill a room the size of a 8 by, or 12 10 by 12 room. So yeah, it's not unusual for that to happen. Let's see. It also can occur in small vessels like aerosol cans. Throw it into a fire, that kind of thing. Cigarette lighters, throw them into fire and run. That kind of stuff. Just if you want to watch them. I'm not advocating that kind of stuff, but hey, you can see what it looks like, or you can watch it on YouTube. Yeah, go ahead and watch it on YouTube. It's much better. They're considered to be high order explosions. Blevies are, and they have the same kind of damage that basically a high explosives have. Explosives basically are the chemical compounds mix, and they're basically explosives are made to cause an explosion. That's the best way I can put it for you there. You have low explosives that result in deflagrations. They move large objects, basically move them around to drop buildings, that kind of thing. And then you have high explosions, which can be used for buildings too, because it's more pinpoint, that kind of stuff. They have chemical explosions. They're similar to what the mixture is in high and low explosives. In low order explosives, they're similar to that, but they're packed under pressure is what it is, like dynamite or something like that that's packed together. They're very stable unless they're exposed to an ignition source. For things like high explosives, you pretty much have to have you have to have an ignition source. That's all there is to it. Say a stick of dynamite, and you can toss it around all day. It's not going to do anything until you put something to it, like a detonation cord that goes into it. What that does is it feeds an ignition source into the dynamite to cause it to explode. So that's you have to have an ignition source of some type. Basically, shattering, splintering, that kind of stuff is what you'll see, and large amount of destruction, and so on. Okay. Now we're going to talk. We talked about seeded explosions. Now we're going to talk a bit about non-seeded explosions. Everybody good to go on this so far? Is this helping anybody?
Yes, sir.
Okay, I'll just make sure I'm not rambling. Good deal. So as far as non-seeded explosions go, we'll talk about the characteristics of those first. And what they have, they're usually within diffused fuels like fuel air mixtures, dust clouds, that kind of stuff is what you'll find non-seeded explosions. And the pressure release rates again are subsonic. They're slower than the seeded explosions. They're slower than the speed of sound, that kind of thing. And because the speed is slower, they're usually not as loud. They won't be as loud. You'll hear a kaboom instead of a boom. But most common type of explosions that you might find are gas vapor explosions, that kind of thing. They're powerful enough to do similar damage as seeded explosions, but generally there's less damage there. Uh, like I say, vapor and gas explosions are the most common. Uh, they're they're usually cause chemical deflagrations, and generally don't see a you don't normally see a detonation when you have gas vapor explosions. That does not mean that you cannot have them. Like I was explaining the thing in Brenham, that ended up being a seeded explosion because it ended up finding an ignition source. Does that make sense? Had to find an ignition source for it. So there we go with that. They're non-seeded explosions generally, and generally don't reach the level of detonation, like I said. They require gas to air mixture to be in the right ranges, right ratios, and once you have an ignition source, an explosion will come up. Basically damages a direct. It's basically the same as the compartment that it's in. It'll follow around. Um, the fuel to air ratio basically is the most important factor into the amount of explosion that you're going to have. If your fuel to air ratio is low, you're not going to get it. If it's too high, you're not going to get it. So therefore, it has to be within the in the upper flammability ranges. If it's going to within the flammability range. If it's in the upper flammability limits, it's not going to do it because it's too rich. If it's in the lower, it's not going to do it because it's too low. Quite simply. Uh, and different types of gases have different flammability ranges, so you have to think about that. And in order to get that explosion, it has to be within those limits. When explosion occurs close to the lower flammability range, it's basically usually the fuel will be consumed, and there's no post-explosion or fire or anything like that. You have the explosion, it's done. When explosion is at the upper flammability limits, not over though, basically the fuel's not consumed, and most likely the fire, there will be a fire after the explosion. So think about the lower, it'll kind of blow it out and it's done. But the upper flammability ranges, it'll ignite stuff around it. So that's what you'll find there. Secondary explosions can occur because the unburned fuels from a upper flammability limits. Secondary explosions can occur, so secondary fires can occur. So that's why you have one of gas meters in there to be able to tell you if your flammability range is too low, that kind of stuff. Which is better if it's underneath, if it's below the flammability range. The most powerful explosions occur when the ratios are slightly higher to that scoliometric ratio. And basically, the scoliometric ratio is the UEL and being in the range of the UEL and LEL to be able for something to explode. The ideal fuel to air mixture, basically, combustion effect will cause fuels to burn, byproducts of combustion. Basically, you're not going to see a lot of smoke or anything like that unless it catches something on fire. Doesn't really, yeah. As far as the closer the explosion happens to that upper ratio, the more degree of energy and damage you're going to have, quite simply. As far as vapor density goes, vapor density affects how the gases mix more than anything else. It's important how they mix. The area between fuel rich and air rich, basically it's the interface where the two are mixing together. And factors that affect the mixing of gases, people walking through rooms, HVAC systems, air conditioning systems for those who don't know what the A means, and fans. Fans can move gases around, that kind of thing. And then ventilation sources, that kind of stuff. Heavier air vapors that settle to lower levels, normally the floor will stay, the the heavier it is, it'll stay lower to the floor, of course, and therefore nothing will really happen. It'll mix with water or anything like that, but nothing will really happen until it's agitated. Like I say, people walk through it or the air starts moving it, then that'll be agitated, and then an explosion can occur. That kind of stuff. Lighter than air vapors, they usually rise up and to the ceiling, and they're susceptible to agitation by negative and positive air flows, that kind of stuff. That's where lighter than air stuff. That's where you'll see HVAC systems carry vapors through a building or something like that, and end up finding an ignition source and causing an explosion. When we talk about fuel migration, basically, it's basically the difference between the distances and leaks and leak locations. And basically, you if you find them there, subsequent explosion can occur. Basically, that's why when you see the fuel migration type stuff, usually they're hard to locate, those kind of explosions. It could be somebody flipped on a light switch when the fuel was all around a room or something like that. That's why you see the commercials that say, go outside and call 911. You usually have to have somebody in there from like the utility company, gas company, something like that to tell you that that's what caused it, was the fuel migration, that kind of stuff. But think about this as an investigator. Subsequent explosions can occur if the migration continues. So therefore you want this stuff ventilated out of where you're at, that kind of stuff. And think about this too. As it migrates out, natural gas and that kind of stuff, LP gas, they are odorless gases. The only reason they smell is because the gas company puts mercaptan in them. And what that does is it makes it stink. Otherwise, this stuff migrating out, like if it's moving out of a building or out of its area, the further it migrates, the less the odor becomes. So it's important to understand that gas can migrate and cause subsequent explosions and so on. As far as blast pressure fronts, we'll go back to that. The pressure front is the direct result of the flame speed and burning velocity like that. And we're not going to spend a lot of time on that. The burning velocity basically is dependent on the composition of the fuel, unburned fuel, of course, the temperature, and basically the pressure of the unburned fuel, quite simply. Turbulence, we talked about people walking through and moving gases around or fans like that. The turbulence are created by obstructions like furniture, walls, ceilings, that kind of stuff too. And basically the problem with that is it changes and alters the movement of the gases during an explosion. So therefore it makes it much harder to detect where it came from. Basically, as the velocity increases, so the intensity of the combustion process. So therefore you have fire, that kind of stuff. So you'll have more fire when the gases start moving around. Heat sources, you can have cause secondary explosions, confined space explosions, and so on. Let's see. As far as ignition sources go, the contact between fuel and air mixture and the ignition source, we've talked about that, so we won't beat that horse anymore. And we talked about venting earlier. Just remember that the pressure wants to be released somehow. So therefore, blast pressure front has to continue until basically all the fuel is consumed, or the gases return to an equilibrium till they're normal. And the greater the ventilation in a compartment explosion, the lower the damage is going to be. So therefore, if you have a big hole, where the gases can get through, your damage is not going to be as much as if you have a little hole where the gases can get through. Secondary fires can be created by ventilations and so on. Venting from detonations don't prevent, though, like seeded explosions, uh, detonations. All bets are off. You don't get that you're going to get the damage whether you have venting or not. So that's the difference in those. That's why when you go in some buildings, you see big vents and that kind of thing. A lot of times that's to let out pressure, that kind of stuff. Like in a chemical warehouse, you'll see the vents on top of the buildings because of that. That way it lets out pressures and so on. Then we'll cover a little bit about dust explosions, and we'll take a break after that. As far as dust explosions, the characteristics for dust explosions, they're usually non-seeded. They're chemical deflagrations. They're similar to a gas explosion or vapor explosion, but they occur in industrial settings like lumber yards or lumber mills, granaries, mines, metal fabricating. I've seen them in cabinet shops and so on. That's why people are in cabinet shops and that kind of thing have to collect their sawdust because it can create a explosion hazard. Grain dust, sawdust, coal, charcoal, plastics, even metal dust can explode. Areas they vary from dust explosions because their particle size. Gas explosions, basically, the particle size are a little bit larger than or smaller than dust. The smaller the particle size, the greater surface area and the more violent explosion will be. That's why when you see gas explosions, the particles are small, so you get a bigger bang for your buck. But you can still see some big explosions. There are some films looking at the videos of some gas explosions and some dust explosions. The biggest dust explosion that has occurred, to my knowledge, was at Imperial Sugar in Louisiana, I believe it was, and I think there's a video of that. But it was sugar dust that exploded. Who would have thunk, you know? Stick your tongue out and get it out. But the whole thing is the whole idea is dust can explode. Concentration, basically, there has to be turbulence that has to unsettle the dust and be in the air, that kind of stuff, and get the dust airborne. The higher the moisture content, the more energy is required for ignition. So when we have days where we have 70 or 80, 90% humidity, we're less likely going to see a dust explosion than you do when you have days that have 40 or even 20% humidity. You're going to see more of these things in areas up in the north, that kind of stuff, where their humidity is not high and that sort of thing. More ignition energy is required for dust explosions than it is for gas explosions, mainly because of the moisture and that kind of thing in the air. And the blast pressure front and dust explosion, basically, it comes from entrainment of the dust. It's going to follow the dust, and basically the dust moves ahead of the flame front. So therefore, your dust explosion, it's not going to be as bad, but you can still have blast pressure fronts from that. So in review, basically, we have to understand the basic science behind how explosions blow up, how they ignite, and how they propagate, how they're made. And we have to have the ability to recognize the difference between the types of explosions, the low order versus high order type stuff. And we understand now the difference between the mechanical and high or chemical explosions, and the difference between the low order and high order damage, that kind of thing. And we know that there's seeded and non-seeded explosions. And we actually have even got to talk a bit about how high order and low order are different, and how you might detect the difference between those. Okay. Any questions about? We're done with dust, or not dust, explosions, that kind of thing. You guys want to take about a 5-minute break, or are you good to go? Or would you rather have a 7-minute? By the silence, I say, let's go. Okay.
Good to go.
Good to go. Sounds like a military man. Okay. Moving on to chapter 5, which is not, to me, it's not as interesting, but it does make a difference in investigating a fire. Whoops, I forgot about that. So what we're going to talk about is the types of classifications of buildings and how they act during fire conditions, and basically we'll talk about how to reduce flame spread and that kind of thing. We'll talk a little bit about fire resistance. We'll talk a bit about some different things. We'll go over that stuff in a minute. As far as fire resistance, as far as fire resistance goes, it's basically what that does is it helps us to understand fire resistance is trying to think a good way to put it. Basically, it keeps the building from burning. It might, for instance, a fire resistant wall can just be sheetrock because the rock inside the sheet will not burn, that kind of thing. So fire resistance is a function of the properties of materials. It reduces the combustibility, it reduces thermal conductivity, basically, and it makes a difference on how dense the material is too. Take when you're starting a fire, for instance, if you take kindling and put it and try to start it on fire, you'll get that to burn a lot faster than you will a 2x4. So therefore, we have to think of fire resistance when we look at that, and the dimensions, how big the dimensions are. A 2x4 will catch on fire a lot faster than a 4x4. Fire resistance basically is the ability to act as a barrier to the fire. Walls, partitions, ceilings, any number of things like that. And when it's expressed, it's expressed in hours, or half hours, that kind of thing, even up to 20 minutes, or as little as 20 minutes. For instance, you can have 1, 2, 3, 4-hour firewalls, 1, 2-hour fire floors, fire rated ceilings, fire partitions, like in a drop down ceiling, you have 30-minute fire partitions there, that kind of stuff. Ratings, they're incorporated in the construction classification, basically in the building code. Fire resistance between requirements of basically fire resistance you're going to have on building beams, columns. Hold on, somebody won't let me go. Hello, I'm in the middle of a class. Can I help you? She's going to have to wait. I'm sorry. You'd think they'd know by now, wouldn't you? This is the admin people. But as far as fire resistance requirements for structural elements, basically the beams, columns, walls, partitions like drop-down ceilings, that kind of thing, floors, ceiling assemblies, roofs, all these things can be fire rated. Even outside walls, in some cases, can be fire rated. So that we don't have a lot to talk about fire resistance, but we do need to understand that there is a fire resistance in them. It all depends on how many people are in there, what type of structure it is, what classification structure. All these things make a difference. As far as building materials go, we know the components and characteristics. It's determined by the various architectural application, basically. What's the building going to be used for? The strength, the density of the materials, what it looks like, durability, uh, any number of things. You just have to know the basic uh, properties of combustibility, thermal conductivity, because remember, metal conducts, water conducts, that kind of stuff, and then a rate of thermal expansion too, how fast it'll move, and basically the effects of heat on a certain material. Common structural materials, basically wood, masonry, concrete, steel. There's still some cast iron out there in older buildings like that, aluminum, uh, drywall or gypsum, plastic. There's a lot of plastic construction materials now. They're even coming up with plastic 2x4s and that sort of stuff too. And then artificial laminate coverings and so on. So it's not unusual to see all kinds of common or different type of components. Wood, basically, the reaction of wood to fire conditions all depends on the surface to mass ratio, really. Moisture content of the wood, that kind of stuff. And basically, we have to understand, and this goes without saying for most of the part, but we have to understand that smaller dimensions, lack of a better way to put it, smaller wood ignites faster, wood loses structural intensity faster than large wood. I mean, it's hard, and I don't know how to say that any better. Large wood dimensions, basically, they're more difficult to ignite. Your structural integrity is maintained much more in larger pieces of wood, and the integrity basically is better with larger pieces of wood. So therefore, when you see a 2x4 versus a 2x6 that's been burned somewhat, you're going to have more strength in the 2x6. The age of the wood makes a difference. Of course, the fire effects on the woods. Older houses, they'll burn slower, but a higher intensity because the resin content is higher than those in those older houses than they are now. If you've ever looked at the difference in burning in a house that was built like in the 60s and the houses that are built today, houses today they will burn so much faster than those built back in the 50s and 60s and 70s because of the way that they're built. Think about oak hardwood. They use them as floors. It might not burn fast because of the density of the wood, but it'll still burn. So it's something to think about. Basically, high moisture in the wood it doesn't ignite easily. It don't burn very fast. And pressure treated things. They pressure treated retardants. They reduce the speed of the fire a lot of times, and but we have to. They might reduce the speed of the fire, but they might not be effective in reducing the fire spread. So we have to think about that too. As far as the main thing that we want to know about wood is the building support system that they give. And when we talk about building support, we also want to talk about masonry. There's different types of masonry, like bricks. Some call them CMUs. I call them cinder blocks. But unit bricks, concrete blocks like stone, clay, gypsum blocks, glass blocks, any number of those type things. Fire resistant and heat effects, masonry walls, they're used to separate different occupancies and that kind of thing. They're usually fire resistive walls are usually hollow, non-rated concrete blocks. They have a fire resistive rating to them. And the concrete masonry, basically they're good for 2 or 4 hours of fire resistance. They rarely lose their integrity during a fire. Try burning a rock, you'll understand what I mean. Now rock can spall and lose surface when they're heated up, but they don't usually burn through. The expansion within the concrete is due to the heat of the fire a lot of times though, because the moisture in concrete. Think of concrete's made out of substance and water. So there's moisture in there. So the expansion of the moisture in the concrete basically can result in the tensile strength breaking down and cause the concrete to start breaking apart. So that's what causes that. Um, Sections of concrete basically a lot of times if they're heated too much they can disintegrate and cause a pitting in there. So when you look at a wall, don't just write it off because it's concrete, because there could be pitting or chipping, that kind of stuff on the surface of it. Like I say, it's not going to burn through it, but it might cause it to take the moisture out and cause pitting or something like that. It'll cause weakness in the masonry and mortar, uh, and rapid cooling, like when we're putting out fires, that can cause it to crack and that kind of stuff too. So when we look at this type of stuff, we want to make sure, especially masonry, that we know that it can be weakened because of the moisture content in masonry. As far as concrete goes, it is a fire resistant material. It's non-combustible, of course. It all varies though on how thick, the concrete density, uh, the quality of it. Is it good concrete, and the load that's supported by the concrete too. What is it? Just concrete walls, like tilt wall construction, and that kind of stuff. So we have to understand those kind of things when we're looking at fire resistance. The depth of the concrete over the reinforcing bars, is it a half-inch thick or is it 2 inches thick? Is the reinforcement bar going to be compromised, or can it conduct fire to a different part of the building? There's all kinds of things that can be asked there. When concrete is compromised, basically, it's usually because of explosions or unprotected openings, that kind of thing. Concrete can spall. Remember, little pieces can fall out, and the difference between basically from heat, it can spall from that. Steam can build up inside concrete and expand and actually cause pitting and that kind of stuff. And what that does is it weakens the structural and reinforcing steel, so therefore your concrete can be weakened by the fire too. So we have to understand that just because it's a concrete wall doesn't mean that it might not have it might not have its full integrity, that kind of thing. And then steel is non-combustible, but steel expands. Thermal expansion causes steel to expand, and normal heat can't really melt steel, but it'll cause that thermal expansion. And what that steel does, it elongates and it expands anywhere from 800 to 1200 degrees. The steel can start elongating. Well, especially if it's unprotected steel, if it doesn't have a fire rating around it, what happens is it can weaken the building. It weakens the steel members, and it all makes a difference. Of course, the size, the opening of the span, the load and spacing on the steel, that kind of thing, and the composition of the steel. How was it made? I know they had a problem with some imported steel several years back, where it was actually expanding at lower temperatures, that kind of stuff. And the shape and configuration of the steel, of course, makes a difference, and whether it'll weaken or not. And then a lot of people don't realize, but a lot of it deals with the duration of the heat too. Is it how long has it been burning? And that's what you want to know. It's a good conductor of heat, so you can get fires in other portions of the building. Basically, and that goes all the way around. So separate fires can occur when that happens. We'll talk a little bit about cast iron. Cast iron, basically, they stopped using it uh, in building structurally. But when you find buildings that the early 1900s on through about the 70s and 80s, you might have cast iron that was used. It's great, but it's strong until it's heated up. It becomes brittle and it cracks or shatters, that kind of thing. And it does that when firefighters put uh, water on it, basically, because it's cooled. The rapid cooling causes the brittleness and the cracking of the cast iron. Uh, think of bolts and connections that secure the cast iron uh, can fail, and that kind of stuff, and they can cause the cast iron to fail too, and cause that to collapse. Uh, most of the construction though has been replaced by steel, so you're not going to see that as much. Now, aluminum, on the other hand, is used much more than it has been in the past. Uh, it residential windows, doors, that kind of stuff, commercial openings, doors, curtain walls, mobile homes. It's to use aluminum everywhere. You have roof coverings, exterior walls, electrical wiring. You don't see too much electrical wiring anymore, but because they figured out that it caused fires, that kind of thing. But you still see some in houses that were built in the 70s and early 80s, that kind of thing. Um, it has a low melting temperature, so it's not unusual to see aluminum that's melted at fire scenes, especially of older buildings and that kind of stuff. Then we talk about more things like gypsum or drywall, that kind of stuff. It's organic product, and it contains high water content that causes it to be chemically combined. Uh, as the heat it goes out on gypsum, the water evaporates and makes the product fire resistant, basically. Now, what can burn though on these things is the paper on the outside of it. It'll still stay in together, but the paper will burn in most cases unless it's fire resistant, and then it has fire resistance to it. Usually it's 30-minute rated, that kind of thing, if it's rated. But as far as it's used, a lot of times drywall or gypsum, it's used to go around steel and wood to create fire resistant, that kind of thing. So it's not unusual to see gypsum even in steel buildings because they use it as a fire resistant, to make it fire resistant. Glass, basically, windows, doors, skylights, all kinds of things that you want to see. We see partition walls, exterior walls. Uh, there's different types of glass. You have ordinary glass. You have tempered glass, heat shrink glass, laminated glass, block glass, that kind of stuff. Remember, glass is basically sand more than anything else. But the whole idea is glass will crack and fall out of its frame unless it's wired in, that kind of thing. Uh, Usually, you see fire rated windows will have, hey, how you doing? Come on over. Fire rated windows will have a little thing in the lower right corner that says it's fire rating. This is Eric back here. He's in our class too. Um, but what this glass does is when it burns, especially if it has like plastic inside it, it'll get wavy and it'll start cracking, that kind of thing. Glass when it reaches temperatures of about 160 degrees, 158 degrees, that kind of thing, it can start expanding and it'll start breaking, cracking, that kind of stuff. The way it start if you see it, if you see the glass or is kind of wavy, that kind of thing, that's when it'll happen too. A lot of fire instructors will teach you that, for instance, look at a light bulb and the light bulb will go towards the flame, that kind of thing. It's not always true, but that's yeah, it will glass will move and move around and start cracking at about 158, 160 degrees, that kind of thing. Doesn't make sense that you can't touch it when it's hot, though, does it? So remember, uh, breaking glass is usually due to firefighting, backdrafts, explosions, that kind of thing. So think about that too when you're looking at a fire. Why was that glass broken? Ask firefighters, did you break this window? It's not a bad thing if they did. It's just the whole idea is you need to find out, was there an explosion, a backdraft that occurred there, that kind of thing. And then you have crazing of glass, which is basically short cracks in the glass throughout the pane. And then you just kind of compare that damage to the glass there to other areas and other pieces of glass throughout the building. Heat release rate for glass, or the type, it basically is based on the type of fuel, and you're not able to really figure the damage of the glass to figure out the heat release rate. Plastic construction materials, basically they're synthetic organic materials. They're used on siding, they're used on floors, they're used on tubs, shower enclosures, pipe barriers, pipes themselves, pipe fittings, lighting, skylights, roofs, sprinkler piping. It's not unusual for that either. And like this building that we're in right now, we have a sprinkler system but since it's a low hazard building, it's put together with PVC pipe, so it's not unusual. Plastic, basically, the fuel load there, it increases the fire hazard because the amount of fuel that's there from the plastic. The fuel is it increases the fuel. It burns hotter, longer, that kind, or faster. It's important for us investigators to know because the intensity at which plastic burns is much higher than that of wood or anything like that. And it burns differently too. You'll find you'll find that you might find dripping or something like that, or if it's burning, it's going to burn a lot hotter and a lot darker smoke and that kind of stuff because it's a hydrocarbon. It's made out of hydrocarbons. Remember, on plastic or PVC, that fire retardant can be put over it, and that'll decrease its ability to burn, but it's not that you don't see it very often. Vapors and that kind of thing are toxic, and that's it for plastics. You know, they're used on everything. I mean, they're even making plastic roadways now instead of using asphalt in some areas. Then we talked a little that said we'd talk a little bit about artificial laminates, that kind of thing. So basically, they're things that are formed together, kind of like interior finishes, floor coverings, structural components like laminated beams, roof decking. The OSB is a laminated material, that kind of thing, and it burns differently from other natural wood because it reacts more aggressively because it's put together with a polymer in order for it to, like glue, that kind of thing. So therefore it'll burn and burn faster, and that's why houses today burn faster than houses did 20, 30 years ago. Okay, so that's all we have on that right there. The next thing we'll talk about is the building classifications. A lot of people have trouble, and I can tell you, I have trouble remembering building classifications, that kind of stuff. So we'll go over them. Think of it this way: you have type 1 and 2, which are fire resistive and you have non-combustible. 1 and 2, 1's fire resistive, 2 is non-combustible. There's a difference between those. Structural members are made of non-combustible materials, type 1 construction. They're non-combustible or limited combustible. So see what I'm saying? Fire resistive. Basically, and they have basically a specified degree of fire resistance. For instance, sheetrock, again, might have a 30-minute fire rating. That would be fire resistive, that kind of thing. Even wood, if you had wood that was, say, logs are fire resistive, that kind of thing, that you might have something like that. Then you have that's type 1. Type 2 is fire non-combustible. It's non-combustible or protected non-combustible, that kind of thing. Structural members are similar to type 1, except the degree of resistance is lower. They're non-combustible. They won't burn. Okay? It's that simple. 1 is fire resistive, 2 is non-combustible. Type 3 is ordinary construction. Now, when we look at that, we're talking exterior walls, a lot of things like the structural members, that kind of stuff. They're non-combustible or limited combustible. For instance, interior structures, structure parts are completely or partially constructed of wood. That's ordinary construction. When you look at type 3, there's I'm trying to think of a good way. Type 3 is like a strip center, just a regular strip center. Most of the time, you're going to find those as type 3 buildings, that kind of thing. Now, type 4 is heavy timber. Heavy timber being like an old church. You don't see much of that anymore. Heavy timber, basically, your dimensions for your wood is going to be like 6 by 6, huge type things. And the exterior and interior walls, the structure members are non-combustible because of the size of them. And usually the interior framing is heavy timber, and basically, like I say, usually it's about 6 by 6 or 4 by 4, that kind of thing. But your structural members are usually going to be at least 6 by 6, where your interior might be 4 by 4 or something like that. Basically, it's going to be larger than type 3 ordinary combustible type things. Then you have type 4, which is wood frame. Exterior walls, bearing walls, floors, they're made either partially of wood or completely of wood, that kind of thing. And type 4 would be like, I want to say type 4 would be, can't even think of one right offhand, but you're basically, a house would be a type 4, where a type 3 would be, it would be like a pier and beam house without bricks, that kind of thing, where you might see type, I'm sorry, that's type 5. We're on type 5, wood frame. I'm sorry. Yeah, we did type 4, which was heavy timber. See, I told you this stuff screws me up. Type 5 is what you would find in a house or something like that. I mean, I'm in a house or something like that. It's wood frame, exterior walls, that kind of stuff. It's like a pier and beam type house, wood frame house, and when we looked at it, type 3 would be like a house with a brick veneer front, something like that. And then you have type, yeah, that's all of them, 1, 2, 3, 4, and 5. And if I confused you all, I'm sorry, but I'm not, like I say, I'm not that great at it. I can figure it out by looking at them, but I always look at the definitions of them because it confuses me. Try to remember as much as you can about them, because for some reason the state likes to put what type of construction is this on their test. So think about that when you look at it.
Hey, Norm, can I ask a question?
Yeah.
This is Washington.
Yeah.
This may help kind of unconfuse a few people between the 3 and the 5. I think of type 3 construction as if you have a 4-walled structure, everything on the outside wall is a true brick, like maybe a warehouse, the older warehouses where it's all from the inside, you can see the brick wall and the structure is brick, but everything on the inside walls is made of wood or a combustible material. And the type 5 construction, which is an ordinary house, you still have the brick facade, but you still have the 2x4 frame structure on the inside and the interior walls. That's the easiest way for me to remember type 3 and a type 5.
Well, thank you for that because yeah, that is a good way to remember it too. I appreciate that. Thanks, Washington.
Yeah, it's kind of confusing, but if you look at it, a lot of people look at building construction from the outside, but you have to look at it from the inside. The fire is going to be on the inside. So it's what's going to burn on the inside outward. That's the easiest way for me to remember. Now, the type 1 and type 2 still confuse me a little bit, but those are so close in comparison, it's almost impossible to tell.
1 and 2 and 4 are the easiest ones to detect because 1 is always going to be fire resistive. Okay, and 2 is always going to be non-combustible. It's not supposed to be able to burn. And fire resistive would be 1 where it'll burn if you put something to protect it. And 4 is always going to be the heavy timber. So if you can get 3 and 5, I can get 1 and 2 and 3, or 1, 2 and 4. I appreciate that.
No problem.
So we're going to talk a little bit about some manufactured homes, like mobile homes, that kind of thing. You have to remember there's different components of a mobile home though. There's a chassis, there's floor systems, wall systems, roof systems, and basically fire behavior factors in like mobile homes, that kind of thing. They're small compartment fires, aren't they? They have low ceilings, composition of floor assemblies. They're closer to you, and they're much harder to look at. They're usually lightweight construction materials, and they burn fast. There was a fire out in Huffman 2 nights ago that killed 3 people. Mobile home fire, that kind of thing. Part of the problem was they couldn't get to it because the bridge over Lake Houston was iced up, but it burned up and killed the 3 people. So we have to look at that. Design changes basically have reduced fire hazards since 1974 because HUD, the Department of Housing and Urban Development, changed what's required on those kind of things. But they still burn faster and hotter. You have prefabbed houses, basically. They're delivered and assembled on site. They're structurally sound, but the fire spread and the rapid fire spread is going to be pretty similar to like a mobile home, that kind of thing. And they're just like anything. They when they're exposed to fire, they're susceptible to failure too. The members and that kind of thing. Then you have modular buildings, and modular buildings basically they come in 2 or more sections. I'm sitting in a modular building right now. They're factory built, and a lot of times they include the utilities, plumbing, heating, that kind of stuff. And they're installed basically the windows and that kind of thing. They go out on site and then they put the windows in them, doors and that kind of thing. And they're designed, a lot of times they're designed to stack on top of each other. How many people have seen been down to Galveston and seen the San Luis Hotel? The San Luis Hotel is a modular building. They were pre-built and stacked on top of each other, that kind of thing. So it's not unusual to see them. They have to meet or exceed building codes, and like I can tell you, the walls in this building are stronger than the fixed building next door, that kind of thing. So they're tough. A they're stronger basically because they're transported to the site, and they'd fall apart otherwise. Uh, Basically, fire travel is dependent on the construction and the method of construction, that kind of thing. As far as log houses go, we're not going to talk a lot about them. Just remember that's heavy timber. They're well insulated, so you're going to have a lot higher than expected temperatures inside those kind of things. And the things that's going to get you in those more than anything else is the varnishes and paints that are on those things. Because in order to keep them viable, they have to put varnishes on them almost annually. So that stuff can burn. Might not be the building itself that burns, but the members itself, but the treatments that they have to treat with, that kind of stuff. So that's what you look at log homes and that kind of thing. We'll talk a little bit about building components now, and we'll start with the roof system. Basically, we know what the roof's for. It's to protect from weather. It's control the interior environment. Different architectural styles of there's different architectural styles. Then fire investigations. Basically, you want to consider the stability of the roof, that kind of thing. Just basically because it could fall on you. You might need to get heavy equipment out to remove parts of the roof. Remember that shingles are made of hydrocarbon materials, so you can get melting and flowing fuels off of roofs, that kind of stuff. You have to look at those things and analyze them. Was that there? If you think the fire started on the roof, was it because somebody put it there, or was it part of the roof itself? They have to analyze what type of ignitable material was up there. Excuse me. Remember, comparative analysis a lot of times you might have to have for those kind of things. You have arched and dome roofs. Basically, they cover a large span. They're usually masonry or wood, steel, that kind of thing. They're usually used to cover circular buildings, that kind of thing. And basically, it's going to be different than rectangular buildings because your fire behavior will be different. The fire will move differently in one of those kind of buildings than in another. Heat currents, they're collected at the highest point of the building because it's come up in a dome, and it's going to collapse much more easily than a rectangular type building. There are roof coverings. I know in Harris County, there are some geodesic dome type shaped buildings that they have churches in, and they have air supported roofs. I know it sounds crazy, but they do. Huh?
Texans training facility.
Yeah, Texans training facility.
Yeah.
Thanks, Eric. But the Texans training facility, like Eric said, is one like that. Basically, roofs can be made of sheet metal, steel, slate, clay, plastic, felt, asphalt. Sometimes you'll see wood shingles, but you don't see those very often anymore. Main reason because once they start burning, so do all the other things around them. But when we look at things like membrane roofs, like the Texas Training Center, we have to think they're made of hydrocarbons. And what the hydrocarbons do is the hydrocarbons can liquefy and spread the fire and make it go across the roof, that kind of stuff. So that's important. As far as fires generally occur during the application of when they're putting the roof on, like if they do like hot asphalt application, that kind of thing, can get fires that occur, that kind of thing, because they use propane torches and that kind of thing. They might fires can even sit there and smolder for a long time, and you can find different things that can cause those fires. Fires might spread across the entire roof before they're even noticed, that kind of stuff. So it's not unusual to find that. But the burning material, when it liquefies, it can drop down through holes and that kind of stuff and cause fires on the inside too. As far as ceiling assemblies go, basically they're concealed building systems, that kind of thing. They're usually made of plaster, gypsum, tile, plywood, fiberboard, any number of things. A lot of them are OSB, the oriented strand board, which is the most common kind to find in houses now. And basically, what you have in these things are floor spaces or spaces between the floors where fire can travel and that kind of stuff. Penetrations that can affect the different flame spread and the travel of the fire. So that's what's important to know about the ceiling assemblies. Wall assemblies, basically, they're used to support beams and trusses and precast beams. Wall assemblies can be balloon construction. Exterior walls, basically balloon construction, you don't see anymore, but what that does is the exterior walls go from the floor all the way to the top of the building, and there's no fire stops, and fire once it gets into it will travel, go all the way up to the roof. It's not unusual to see that on a balloon construction type building. The type of structural framing is used in some multi-story wood frame, but not very often. But remember, balloon construction is continuous from the foundation to the roof. You have platform, which is more common. Platform, basically, they're not continuous to the second floor, that kind of thing. You'll have a stopping point from the first to the second floor, second to third floor, that kind of thing. They're just not continuous beyond each floor. So therefore, you have a fire stop somewhere between the floors and that kind of thing. And then you basically it's built one is built on top of the other. There's basically, when you're going into a fire, just check load bearing walls and that sort of thing to be sure that they're safe to get in there. You have lightweight construction. Again, look at lightweight construction on some of the videos that we have. There's engineered I-beam plates, plate connected wood, floor trusses, which is really common now. I mean, my house was built in 1998, and I have truss beam construction in my house. So I mean, it's not unusual to find that. Let's see. It's used mainly, lightweight is used in small commercial buildings, warehouses, houses, apartments, that kind of thing. And there's truss construction, which is little triangle type things that are they're known. They are the strongest geometric shape, but they will burn and cause destruction of a structure much faster than any other type of beam. Basically, they're an integral part of the whole system, and basically, trusses are dangerous for firefighters. They're dangerous for fire investigators. So we have to make sure that we know if it's truss beam construction and if those trusses have been compromised. As far as floor systems, basically, they're to put stuff on, to walk on, to put dead loads on, that kind of thing. And that's what we have to think about when we look at floor construction. Is there a dead load on that floor? And they might be, depending on the fire code, they might be required to be fire resistant. I can tell you, if it's in a high-rise building, anything over 75 feet high has to have 2-hour fire floors. So therefore, they have to be fire resistant between each floor. Each one sits on its own. As far as concrete floors, they usually have wire mesh that basically that provides stability, that kind of thing. They might be lightweight concrete that supports that, the floor span, that kind of thing. You have steel floors that have open bar joists, and what that does is is it supports like a steel deck, that kind of thing. And then you have the lightweight steel joists that are and trusses that are the just like the wood trusses, and they too, the geometric shape of them makes them stronger, but they're more dangerous. Foundations, basically, we're going to talk a lot about that. The interior finishes, a lot of times what causes fires to spread is interior finishes, and what they do is they increase the spread of the fire and the result of fire deaths and that sort of thing, because as the fire grows in size, so does the intensity of the fire, and you can have flashover a lot faster, that sort of thing. Things that the chemical composition of the material basically is what influences the fire spread on interior finishes, and of course the geometry, where it's spaced, what the shape is, and that kind of thing. And then you have things like compartmentation. In every building, you're going to have some type of compartmentation. There's barriers that are designed to keep flame, smoke, and heat from spreading from one room to the next. That's why you have walls. That's why you have fire doors, extra walls, partitions, fire stops in walls, that kind of thing. That's to keep the fire from moving from one area of the building to the other, one floor to the other, that kind of thing. If in large warehouses, basically, you might not see them in those, but what they'll do a lot of times is keep the fire from spreading vertically or horizontally, making a room out of something. Most floors, ceilings, and walls, they act as a fire barrier, but they'll slow the fire down, but they might not be rated. So think of that when you're looking at them too. Remember, ventilation causes a lot of fire spread and flame spread, and ventilation, building construction and ventilation, airflow makes a big difference in fires in a big building. You have to be able to identify the airflow during the fire in relationship to the building construction. Air handling units like HVAC units, they move air from one portion of the building to the other, and in a lot of cases they're required to have detection systems specifically on an HVAC unit to turn off the air handler so it won't move fire through anything or through the building or smoke through the building any longer. Think of concealed spaces, that kind of thing. There's spaces that are there for piping, for chases and that kind of thing, and they can be both vertical and horizontal. Ducts run through them, not the quacking kind, but the air ducts, that kind of thing. And ignition sources that go into chutes, like laundry chutes or trash chutes, can cause a lot of damage and fires, that kind of thing. Now, I don't have much more on building construction and that kind of thing, and but it's something that we have to cover insofar as that goes. So in summary, that basically a firefighter or a fire investigator, we have to be effective, we have to have a working knowledge of the building construction. You don't have to know all about it, but get someone there that knows about building construction and what's going on. I'll give you an example. There was a building in Seabrook. It was a brand new hotel. I think it was a year ago or 2 years ago. Caught on fire. We couldn't figure out why there was fire all throughout this building, because it was a sprinkler building. Duh, what's the problem? Well, what happened was the fire started from what is that stuff that you put on the ground? The mulch. It would end up there was mulch stacked up against the building, and the building construction on the outside was combustible on the outside, and it went up a false wall and got to the roof. Kind of weird, but yeah, it burned up that hotel, brand new hotel. Who would have thought that it would have been started by mulch, So just saying, you never know what starts the fire until you start looking at all the there's always an answer there somewhere. But knowledge of building construction, it can assist in the determination of the origin and cause and the spread of the fire more than anything else, and being safe when you go in there as an investigator. So what we've talked about is fire resistance, what that is, and what the most commonly used structural components are, and that kind of thing. And we even talked about building classifications, the type 1, 2, 3, 4, and 5 construction types. Basic classifications is what they are. As far as we talked about construction, mobile homes, prefab, modular buildings, and so on. And basically, what the building components, what effect they have on us as investigators, and how we might be able to use use these things as an investigator, how that's going to help us. Okay. So what we're going to do next is we're going to go over. Anybody need a break? Let's see. We're going to talk about the car fires. It's chapter 8. Is it 18? What skill did we do? 4? Sorry about that. Let me find the right one here. Skill number. Sorry about that. Yeah, learning activity 4. We're going to go ahead and go over that first, because that's the one that we did. And when you look at these photographs and that kind of stuff, you will find different questions and so on. So when you look at the first photograph there, I'm not going to give you the answers, but I'm going to show you. I'm going to tell you some of the things that you see there. And we talked about it during explosion dynamics and that kind of thing. In photograph 1, you have walls laying on the ground, and you have burned 2x4s inside the building. You think about what we talked about, your ranges, your upper and lower limit ranges, and look at that and tell me, was that a high order or a low order? You guys can go ahead if you want. Okay. You don't have to raise your hand. Just throw it out there. But when we look at this, the reason why we would call this a low order explosion, deflagration, that kind of thing, is because when you look at it, your walls are laying on the ground, aren't they? And you have burned members inside. So you know your upper flammability range was there because of the fact that all those burned members are inside, right? So you're going to have your upper flammability range. So therefore, you can see there was an explosion, more than likely a low order explosion, a deflagration, and what that did, it caused, it was in the upper flammability range because of the burning members inside the house, that kind of stuff. Okay. When you look at number 2, this one's a little different because it's still, when you look on the outside again, you can see walls that are on the ground, can't you? Number 2. I'm not gonna. You guys have this in y'all's presentations and that kind of thing. But number 2, again, walls are on the ground. You have burning inside the building, so therefore you know your upper flammability range is there again. Okay. Your scoliometric's not there really because the whole idea, and it's not number 1 either, because you didn't have a detonation. You had, again, a deflagration there. You see what I'm saying? So therefore, when you look at that, you're going to have that. Number 3 is tricky because it's meant to be tricky because it's something different. That, more than likely, was when you have to look at a lot of different things on this one. When you look at the window, look at it closely. Was the glass inside or outside? That'll tell you if somebody broke that window in or out. Makes a difference, because I'm going to tell you what it is because I'm going to give everybody credit for it. But what that was a Molotov cocktail that was thrown up against the building. Okay? That's why you have the scorch on the outside of the brick, that sort of thing. And if you look, there was probably another one thrown in that window, because the glass, there's no glass on the outside sill. There's glass on the inside sill. Remember these photographs, and I get a lot of people that tell me, I can't tell in a photograph. You know what? Sometimes that's all you have is a photograph. So I don't want to hear people making excuses. Tell me what's there. Don't tell me I can't tell because I can't see it. Because the thing is, when you're on the stand, you're not taking people out to a fire. So you're looking at it going, oh, wait a minute, I don't remember what that is. So when you're looking at it, say what's there. Say what you see. I see a scorch mark there. I see a window that's broken. What could have broke that window? What could have let that scorch mark? More than likely, that's going to be a Molotov cocktail. I can tell you that's what it was. But the window's broken on the inside, and so on, because that's all we have to go with. So the guys that like to say, I can't tell because of the photograph, that's all you have, because we're doing it this way. When you come out for burn day or for skills day, we have a burn cell that will show you. If you decide you want to ride with one of the investigators, they'll be able to show you these things, and you'll be able to see them. But for now, being an online class, all we have are photographs that we can show you. Okay. The last one there. Look how everything's splintered there. That's a big clue, isn't it? The big clue there is there was a detonation, wasn't there? So therefore, look, there's nothing burned on the inside of the house, really. I mean, nothing that would sustain burning, right? So therefore, your scoliometric range was there, wasn't it? Because it's nothing burned inside. It's all burned on the outside. When you look on the outside, you have debris across the roadway there. You have trees that are burned on the outside. And when you look inside, you might be able to make out towards the back of the house, a crater, that kind of thing. The back right part of the house, there's a little bit of a crater. So therefore, you have detonation, which would tell you it's probably high order, and you also have a little crater back there. So therefore, you're going to see this was probably a detonation, and it was probably a detonation from something like a gas explosion or something like that, because you can see it looks like pier and beam construction, but there ain't nothing left of it, and nothing's burned on the inside. So when you look at when you do these, take and answer the questions, as there are. What type of damage is in the photograph? That kind of stuff. Okay, and so on. So don't make them difficult on yourself.
Hey, Norman, I got a question.
Yes, sir.
It's Washington again. Just so I can clarify a couple things, because I was one of the ones that put something about the picture. Back on number 3, I can understand that it's sometimes that's all we have is a picture, and I don't know if you were on that scene or not, and it may be easier to tell if you're there, but I couldn't tell if there was glass on the inside or the outside from the picture, and looking at the scorch mark. I put on mine that there possibly was a pipe or an electrical conduit coming out, because it looks like at the bottom of that scorch mark there's a hole in the brick. I wasn't sure. It was hard to tell. I didn't know if I was looking at it right or I was just way off or what. And I guess on number 4 with the scorchiometric scale, can you help explain that to me a little better? I'm still a little bit confused because there's obviously no burning inside the home. I can't tell the outside area that is scorched obviously is part of the yard. I couldn't tell if that was part of the house or not. But if you have the burning on the inside, it's within that range. If you don't have it on the inside and you just have the blast, you're saying it's outside that range, correct?
All right. Yeah, you're going to see that more so. I can't tell you that's 100% every time.
Yeah.
Because nothing's 100%. But the whole idea is when you look at it, your scoliometric range, your when we look at it, it's defined in the book and the glossary, but it's not really defined in the chapters per se. And NFPA 921 will define the scoliometric range for you too. Let me pull that up and I'll read what it is here.
Yeah, I've got it here somewhere.
That way it kind of makes a little more sense. And I'm pulling it up as we speak.
Okay.
So when we're doing that, if the air fuel mixture, basically I'll read this portion of NFPA 921. It's something. It's the air fuel mixture has an optimum ratio at which the point of the combustion will be most efficient. That's going to be your scoliometric. It's going to be your detonation point. The ratio occurs at or near the mixture known as the scoliometric ratio or range, that kind of thing. So therefore, when you get a detonation, your mixture is going to be it's going to be between the UEL and the LEL. So therefore, your scoliometric range will it has to be there for the detonation to occur. Does that make sense?
Yes, sir.
So therefore, you want the burning basically. Basically, there's no used or unused air. Basically, what it does is the explosion happens there, and it's because it's the detonation is what it is.
Okay.
Let me see if I can find anything else on that. Basically, it causes the maximum heat to air exchange or ratio. Your HRR, your heat release ratio, is higher. Your scoliometric range, it's higher once it's there. That's why you might won't get fire on the inside, but you will on the outside.
Okay.
Okay.
Yes, sir.
Best way I can explain that. Sorry about that. Hope that helped. If not, sorry about that. Okay. So, if you got paperwork and that kind of stuff, get it back to me if you want to ride with any of the investigators. They're busy most of the time. They've got a caseload of about 40 to 60 each. So they're busy. You'll be doing something. If you're not going to a fire, which they get a lot of fires, but you will be doing something. You will go to. You'll either like today. They're at a. What is that thing called? Oh, autopsy. they're at an autopsy day. They might be out on fires. They might be going to pick up suspects. You never know. So it's doing interviews. They do the whole gambit here, and so we even serve our own warrants. So it's kind of a little different than others.
Norman, can I ask a question along the lines of the paperwork?
Yeah.
I'm full of questions today. On the one of the forms is it has to have a witness and a notary. Do we need to sign that in front of a notary? Do we need to sign that in front of y'all, or do we just need to get it witnessed, or
Go
both?
ahead. Go ahead and just get it witnessed and put it back in, because I've never had them do the I've never had them. I think they'll notarize it themselves.
Okay, so we can just get it witnessed and scan it back into you. Yeah,
and I'll send it. I have to send it over to HR, and they make sure everything's done. If not, I'll send it back and tell you what needs to be done with it.
And it asks for a date on here of a ride, but we can do that later. We can figure that out with y'all, correct?
Yeah, go ahead and send it when you do that. Send me a schedule of your availability, and I'll give that to Scott. And Scott, he arranges all the ride-alongs.
Okay.
They work. You can do AM, PM, or either one. And if you want to go more than one time, that's fine too. So not a big deal.
Okay, sounds good.
Okay. Anybody else have any questions? I guess your microphone's the only one that works here, Chuck.
I had a question. What are the times of ride outs? What are the hours?
It's during your availability.
What is it?
Quite simply, you just send me what you're available. They work 6A to 6P and 6P to 6A. You have to think about it though. Once you get on there, if you get hung up out on a fire, you might end up being out there for, you could be out there 10 hours or 12 hours or 16 or 18 hours. So
I got you. And do we meet y'all out there at Atascocita? Is that where your office is?
actually, we have two offices. We have one here at Atascocita, and if you're closer over to the west side, we have an office in out of 290 in Hollister too. So we have investigators in both offices.
All right, thank you.
You betcha. Anybody else?
There was a question in the group chat about the stoichiometric ratio.
So how do you say that?
Stoichiometric.
Oh, okay. There you go. Okay. The book refers as a ratio perfect or high on those high order. So it wouldn't be for a higher ratio. Would it be for a high? Yeah, it would actually. Would it be for a higher ratio? The answer is yes. 3 to dryer fryer, huh? No, sorry. Let's see. Anybody else have any questions? That I can actually answer? Okay. Let's see. All right. Well, hopefully this this helped. And it does help. We'll load it up for those who want to review it again and say, hey, you said, sorry, but sometimes I say wrong. But the whole idea is for everybody to look at it. Some people it helps to have these, so we're going to keep having them. And fortunately, it didn't go off today, and it lasted 2 hours, so that's not too bad. Next week we'll go over a couple more skills. Think of these skills more as a critical thinking skill more than anything else, because as firefighters, we don't have to do a lot of critical thinking because we go put the red stuff on the wet stuff, or wet stuff on the red. You see, I don't even know anymore. But now we put fires out. You don't have to think about you don't have to think as much about how it started, where it started, that kind of thing. So when you're looking at the photographs, when you're looking at these things, do some critical thinking. Okay, when I look at this photograph, okay, well, is the scene secure? Well, I see tape on this side. Do I see tape on the other side? I see people standing in the video or in the photograph. Why are they there? I see cars parked in there. What are they there for? Are they part of the scene? These bodies laying on the ground, how come I don't see any security around them? There's stuff laying up on the hood of the truck. Is that evidence? Think of those kind of things in your head, because you have to ask a lot of questions as an investigator. And that's the only way you're going to be a good investigator, is to ask questions. So when you look at these photographs, think of things like that other people wouldn't say. Like, say, are those people belong in this photograph? Is all that stuff stacked up in front of the door? Were they trying to block an exit to hurt somebody? Think of things like that. Not just look at the picture and say, well, I see this. Look at the background. Look at, say, for instance, you see a house fire. Okay, do you see any burn patterns? Well, I see one on the outside left front of the house, and it looks like a V pattern. That kind of stuff. So look, when you're looking at them, be very colorful in what you're saying. And then when I give you feedback on those things, I'm going to give you feedback, not that you're wrong, because you might find things that I didn't find. You'll find things that the people from ISTA didn't find, that kind of stuff that came out of the book. So it's going to be different on a lot of them. Don't, just because I'm giving you other perspectives does not mean it's wrong. Okay. The only way that you're going to fail these things is if you're just way off base. If you've missed the whole reasoning behind them, then I'm not going to give you a bad failing grade. But each one, I'll get with Chris. But each one you should have 2 tries at. After I give you feedback and that kind of thing, go back and look at it again. And the same with tests. You should have two tries at the test too, each test. Has anybody had to retake a test? If you have, but it's letting you do it, right? Yeah. Okay. If you've had to. Okay. So the skills you should be able to resubmit once I send some stuff to you too. Okay. So TTFA. See you guys next time. Right? Same bat channel, same bat, whatever it is. All right. Thank you. See y'all later.